Hello, and thank you for your time and your interest in my talk today. I'll take you through reconstructions of the Soldiers Cap Kuridala Basin in northwest Queensland. The inset map shows the location of the main map. My approach in this region is very much focused on integrated interpretation of the seismic data and potential field data, and this is constrained by outcrop geology, geochronology, and other key data sets. The talk today will start by looking at the data, mainly stratigraphy and seismic data. Then we'll look at the schematic reconstructions and finish up with implications for mineralisation. The Soldiers Cap and Kuridala groups are exposed in the southeast of the Mount Isa province within the Eastern Fold Belt, the Etheridge Group to the east in the Etheridge province, and in combination, we have over 600 kilometre width to this basin system. The interpretation that I'll show today is based on a large number of these seismic lines, but today I'll just show IG1, which provides the link through to the Etheridge Group, and a segment of M6, M5 here at the southern edge of outcrop around Cannington and Osborne, and that's the line that I have reconstructed. Tommy Creek sits in here. I'll mention that briefly in terms of stratigraphy. So starting with stratigraphy, in the west, the Isa and Calvert superbasins are separated by significant unconformity associated with regional uplift and emplacement of the Sabella batholith during extension. During this period, Kuridala and Soldiers Cap groups are deposited in the Eastern Fold Belt. They're broadly divided into three main units, with the middle unit being coarser grained and quartz rich and associated with this main Sabella event. There's one location where the Kuridala-Stavely contact is interpreted as stratigraphic. Elsewhere in outcrop, we typically see the middle or upper units in structural contact with the Stavely across low-angle detachments. There's a distinct suite of high-iron tholeiites associated with this package, which is also present to the east in the Etheridge Group. The base of the Etheridge Group is not exposed. The package is similar in age overall, but also includes some younger units. These younger units are also present in the Tommy Creek block back in the Eastern Fold Belt. Work by Griffin and colleagues provides evidence for this younger package in the Soldiers Cap group area. This is based on detrital zircons in drainages just off the edge of outcrop. And these zircons are from a juvenile mafic source. The main pulse of extension is likely to be the Sabella event, but the fact that bimodal magmatism continues throughout this period through to around 1620, and also the fact that at 1605, metamorphic conditions indicate a very high geotherm, and that requires additional heat input. So this suggests extension started around 1680, but continued episodically through to about 1620. Looking now at the seismic data, IG1 is about 400 kilometers long, vertical scale 20 seconds two-way time, or 60 kilometers. Soldiers Cap group is about 5 kilometers in thickness, 5 seconds in thickness, or 15 kilometers. Etheridge group is a little bit thinner on this line, but is also about 15 kilometers on adjacent lines. The underlying crust of the Numil province is dominated by relatively thin, low-angle fault blocks and crustal scale structures. Jumping south to the M6, M5 line, the Kuridala and Soldiers Cap groups are about 3 seconds in thickness, or 9 kilometers, and this southwestern edge of the basin overlies the west-dipping Gidja suture, which forms the boundary between Mount Isa and Numil crust, and is interpreted to have formed at 1850. So we have a remnant basin that still has 9 to 15 kilometers of sediment, overlying crust that's dominated by low-angle fault blocks, suggesting it has been highly thinned in the past, and also overlying the Gidja suture. So getting on to reconstructions, at 1620, around the end of the period of extension, we had a very thick basin, and our geometry here that I've interpreted is based on the present day seismic. We can see this wedge-shaped geometry to the thick Mount Isa crust, and the thinner tapered wedge to the Numil crust, which is much thinner overall, and is dominated by low angle faults. The high iron tholeiites are represented by the green lines, and they have a morb-like composition. George Gibson and colleagues have suggested that the crust had breached or was close to rupture based on the composition. The basin thickness that I'm showing here ranges from 10 to 20 kilometers, and this is based on the preserved thickness from the seismic, in addition to the missing stratigraphy, and also the fact that the metamorphic conditions at surface here around the southern edge outcrop indicate the present day surface was 10 to 20 kilometers deeper during peak metamorphism. Now, let's take another step back in time. We go back to 1675. This is when the middle unit was deposited coeval with the Isabella batholith, and this is the approximate timing of Broken Hill type mineralization. Now, it's hard to constrain just how thin the crust may have been, and we don't know whether extension proceeded to the point of exhumation of either the underlying mantle or lower crust, or whether we may have even had limited seafloor spreading. But what is clear to me from these reconstructions is the importance of structural inheritance. The geochronology, which originally formed about 1850, localized this depocentre, then in turn this depocentre localized the later Eisen deformation from 1610 to 1500. Looking at the lower cross-section, we can see how the inversion was controlled. When you think about shortening this crustal section, we'll start with reactivation of the normal faults, and then as shortening proceeds, we start to have a room problem in this overlying basin. We can expect larger scale displacements along detachment faults facilitated by the carbonates, and the numal crust will be thrust beneath the thicker, more buoyant Mount Isa crust and lithosphere. Now, just briefly looking at Broken Hill type mineralization. So it's sediment-hosted zinc, lead, silver mineralization, generally interpreted as exhalative. Host rocks are typically oxidized clastics with exhalatives, mafics, and ironstones in the sequence, and we're looking for a network of faults to act as fluid conduits. We can expect those conditions throughout this depocentre. However, a key point is that the geotherm is going to be very high in this area of thinnest crust. So that's going to impact the redox reaction that's generally inferred to be responsible for lead and zinc deposition. It's less effective over 250 degrees C. So we're going to look for the areas that have a lower geotherm on the margins, and they will be more prospective. The challenge now is to assess where these margins are located in the present day shortened depocentre, and also to consider where Cannington may have been located in this original depocentre. This is preliminary work, and for me, it's raised more questions than it's answered. A few thoughts to leave you with today. Structural inheritance and reactivation of basement structures have played a key role in this area. Geochronology is a prime example. What we see today is represents closure of this basin during the Eisen orogeny, and the original 1850 suture may have looked very different. By 1620, we'd set up a structural framework that controlled later shortening. So whether you're looking for sediment-hosted synextensional mineralization or any younger structurally controlled deposits, it's key to understand this crustal architecture and extensional fault system. Thank you.